Hi everyone, so welcome to PHY101. Today we work on tutorial sheet 5, which is work, energy and power. Okay, so I hope everyone is set to enjoy the tutorial for the next 1 hour and a few minutes obviously. Yeah, so tutorial sheet 5, question 1. I'm going to read it out for you guys. So we have a situation which says Leandro wants to have a bit of fun with her wagon. She puts her 12 kg baby sister, Walusi, on the wagon and pulls it across the floor using a rope at an angle of 22 degrees above the floor. Using the spring balance that her mom uses to weigh things in the kitchen, Leandro realizes that the tension in the rope is constant and has a value of about 40 newtons. So we are being asked specifically to use the work energy theorem to find Walusi's speed after being pulled 4.0 meters across the living room, and we've been given the coefficient of friction to be 0.2 and the weight of the wagon to be 3 kgs. Okay. So the first thing that we have to do is to always have a picture illustration of what is happening so that we are able to grasp the concepts, and then after that we can proceed with the calculations. So in our scenario, we are being told that Leandro has placed her sister in a wagon, so let's take that to be our wagon. And this is Leandro's sister, Lucy, who weighs 12 kgs, and then the wagon weighs 3 kg.
There is mass reflection here, so you start from the middle and go on the other side.
Okay. Yeah, so let's just change the view. We've been advised that there's some reflection here, so you guys cannot see very well. Okay, so question 1. Okay. So this is the wagon, and then this is Leandro's sister, who weighs 12 kgs. The wagon is 3 kg itself. Okay, and then she's pulling the wagon at an angle with respect to the horizontal, which is 22 degrees. And then after measuring the tension in the rope, she realizes that the rope has tension which is equal to 40 newtons. Okay. So we are being asked to find the speed after the wagon has moved some 4 meters across the living room. And in this case, we've been given the coefficient of kinetic friction to be 0.2. And what other variables have we been given? Okay, that's it. So we've also been told to specifically use the work energy theorem to come up with a speed that is required to move Leandro 4 meters across the room. So, applying the energy conservation law, using the energy conservation law, we know that the total energy, the initial total energy, should give us the final total energy. And the total energy in this case is given by the work done plus the kinetic energy and the potential energy that is contained in our system. So if we look at our system here, our initial total energy is given by the work done initially plus the potential energy initially plus the kinetic energy initially. This should give us the work done final plus the potential energy final plus the kinetic energy final. So looking at our system, this system is starting from rest and it has to move 4 meters. Therefore, the kinetic energy here is 0. The initial kinetic energy is 0 since it's starting from rest. The potential energy here, we know that the potential energy is given by mgh. In this case, this thing is being dragged on the horizontal surface, so therefore h is 0 in this case, and as such the potential energy is also 0, so this reduces to 0. And then what is remained is the work done in order to move that. So we have the work done, okay, in moving the system should give us, when we look at the right hand side, we've been told that there's okay, at the right hand side here, we can also tell that the potential energy, since this thing is still moving on the horizontal, the potential energy is also 0 because the height is 0, so that reduces to 0. Then the kinetic energy is given by half mv squared plus the work done to move this thing against friction. So work done against friction. Okay. So let me just erase that. Okay. So we know that the work done initially, the total energy initial is equal to the total energy final, and then we determine that the only thing that remains on our left hand side, we only have the work done that is required to move the system, which would give us the kinetic energy plus the weight that is required to move against friction. Okay, so in this case, the work done, we know that the work done is just given by W is equal to the force times the distance. Okay, and we know that the kinetic energy is given by half mv squared. Then the work done against friction, in this case, the work done against friction is given by the friction force times the distance. So we have 3 quantities that we replace in our equation there. So to replace, let's say that this is 1, and then this is 2. So if we substitute 2 into 1, we can see that on our left hand side we have the force times the distance should give us the kinetic energy, which is just half mv squared, plus the work done against friction, which is the friction force times the distance. Okay, so we need to find V as our statement of the problem. Okay, so how do we find V? We have the force, which is given through the tension. So if we look at our system, if we draw a free body diagram for our system, so if that is my X and that is my Y, you can see if this is the mass that is being dragged at an angle 22 degrees. Okay, and then there is a tension in the rope that is just given by 40 newtons. So to resolve the tension in the rope, we can say the X directional tension here is just given by T cos theta, and then the Y tension, the Y component of the tension is given by T sine theta, where theta is just 22 degrees. Okay, and we know that this is at an angle, so therefore if we sum all the forces that are acting Okay, before we proceed to that, if we look at the formula for weight, which is the force times distance, the force is the horizontal force. So therefore, in this case, our horizontal force is given by that. So when we break down the components of T, which is being put at an angle, and replace it in our force times distance equation for work, we can see that that reduces to T cos theta multiplied by the distance is equal to, because this thing is moving in the horizontal direction, so our force is now replaced by the horizontal component of the tension. That will give us half mv squared plus our frictional force. We know that our frictional force is given by Ff is equal to mu, which is a coefficient of kinetic friction, multiplied by the normal force. Okay? So we replace that by that. You have mu Fn, then multiplied by the distance d. Okay? So if I erase that, okay. So, but what is Fn? We know that Fn is the normal force which is pointing upwards, and the downwards, if that is our system, and downwards is given by just mg, which is the weight of the system. Okay, and the system, remember that the system comprises of the gear and the wagon. So therefore, summation of forces in the y should give us the normal force, which is acting upwards, because this is our, we are taking upwards to be positive, minus taking downwards to be negative, minus mg, which is the weight. This should give us, since this thing is not accelerating in the y direction, this should give us 0. Therefore, the normal force in this case is just given by mg. So if we replace this into our energy conservation equation here, what we'll end up with is T cos theta, okay? We'll end up with T cos theta multiplied by the distance. So this is just the work done, which should give us half mv squared. Remember that this is the kinetic energy, plus the work done in moving our system against friction, which is mu, but Fn is mg, so replace Fn by mg, then multiplied by the distance. So what we have here is now to just make v subject to the formula here. So taking everything on the other side, so we'll have mv squared is equal to T cos theta multiplied by d minus mu mg multiplied by d. Okay, so if I multiply throughout by 2, I'll end up with a formula v squared and divide everything by m. I'll have v squared is equal to 2t cos theta multiplied by d minus 2 mu mg, okay, multiplied by d. Everything is divided by 2. So at this stage, I know what my v is, and I've been given all the parameters, so I just have to replace all the quantities that have been given by the values that they have in order for us to find the speed that is required to move the wagon together with the girl in it, the distance of 4. The tension is given by 4, so that is just 2. Tension was given by 40, so that is 2 by 40. Cos theta is 22. That's the angle that it makes. times the distance is given by 4 minus 2 mu, here the coefficient of kinetic friction is given by 0.2 m. Remember that m is a collection of the gear and the wagon, so together they make 15 kg multiplied by g, which is 9.8, times d, which is 4. Everything is divided by, it's divided by m rather, because we are dividing by m and multiplying everything by 2, so everything is divided by m. M is just given by 15. Remember that m is the mass of the system, and the system comprises of the gear and the wagon. When you do all the analysis here, we will find V to be, so after doing the calculations, if I punch that in my calculator, I'll find V to be equal to 2.02 meters per second. So this is the speed that is required to move the system a distance of 4 meters rather, around the living room. I hope that is clear. Okay, so since I cannot hear your responses, I would appreciate if you leave your comments down the comment section below. Remember to make positive vibes as well as negative ones, though we would appreciate if you guys can help us give a correct feedback so that we are able to help you in the correct possible way. So we proceed to the second question. Okay. A moment. So in our second question, I'll read it out for you. We have a roller coaster car that is moving on a frictionless track as shown in the diagram. So this is my diagram here. So we have a roller coaster car. It's starting from the top and then it goes down and up here. Okay, so that's the horizontal. Okay, so we are being told that a roller coaster car on a frictionless track, as shown in the figure below, starts from rest at the height h. So the track's valley and hill consists of circular shaped segments of radius r. So these are circular segments that have our radius r. The same thing here applies. So that's our radius r. Yes, so the first question here, we are being told to find a symbolic expression for the maximum height. So we need to find the maximum height h max from which the car can start so as not to fly off the track when going over the hill. So as the car starts here, we need to find the maximum height such that when this car starts, as it goes down the valley and up the uphill there, it does not fly off, but rather remains on the track. So we need to find the maximum height that we need to give this thing. So remember that our velocity, our initial velocity is given by 0 since this thing is coming from rest. So how do we proceed solving this? Remember the topic that this question is based on is work, energy, and power. So therefore we proceed using the work energy theorem. So by the work energy theorem, we know that the total energy that is at the initial point should be the total energy at the final point. So this is the conservation law of work. Okay. Now, the total energy, if we say, let's start from this point, the initial point, let's call it A, and then let's call the uphill point as B. So if this is the total, if this is the initial starting point, we know that the total initial energy is given by kinetic energy plus potential energy. So initial should give us the kinetic energy final plus the potential energy final. Okay, so starting from A, if we say from point A to B, if we analyze our motion from point A to B, B being the uphill, we can say that at point A, the kinetic energy is just 0, because that's our initial starting point, and it's 0. Remember that kinetic energy is given by Ke is equal to half mv squared. In this case, the reason why kinetic energy is 0 because our initial velocity is 0. So if that is 0, then the kinetic energy is 0. The potential energy, remember the potential energy is also given by Ke is equal to mgh. In this case, we have h because that is starting on a higher uphill. Therefore, what will remain initially here is the potential energy initial is equal to, when you look at our total final energy at point B, we still have the kinetic energy final. So kinetic energy final plus the potential energy final, because this thing has a height. So we still have the potential energy final. In this scenario, we are neglecting friction, so we want to consider the work done by friction. Okay. Now, so what we have remained from A to B is simply at the top here, what is remaining is the potential energy, which is given by mgh at point A is equal to the kinetic energy at that point, which is given by half mv squared at point B, and the potential energy at that point, which is given by mgh at point B. Okay? So, when we look at the parameters, what have we been asked to find? We need to find the maximum height that is required to give our car, which is starting here, or rather a roller coaster that is starting here, a maximum height such that as it travels through the uphill, it does not fly off, rather it stays on the track. So if you look at our final equation here, we know that we have the quantity m, which we can just cancel out because m is there. So what remains here is g. Remember, HA is at point A, and that's the maximum height that we need to find, so we can just say H max is equal to half. What will remain there is VB squared plus G. HB, when we look at our diagram there, we are being told that the segments that the valley and the uphill are making, they are making circular segments. Therefore, the height that our uphill has is just simply the radius of the circular segment that it's making, which is just r. So h in this case is r. Okay. So we cannot proceed in dealing with this equation because we did not know what VB is. So how do we find VB? We have to figure out another way to find VB and then replace it in this equation so that we find the maximum height that is required for our system to remain on track. So how do we proceed? So we proceed by finding the velocity at that point by analyzing our roller coaster as it reaches that point. So I hope you've written this, so I can just take it off. So analyzing our motion at that point, so if this is our uphill and then our roller coaster is here, we know that the forces that are acting on our roller coaster is given by the weight itself, which is mg, and then there is a normal force, Fn, that is acting upwards. But remember that this is a circle, and therefore the acceleration of the system will be pointing towards the center, because acceleration will always point towards the center, and the center is here. In this case, it will point away, which they are towards the center on every respective point. So at this point, it's going to point that side. At that point, it will point downwards. So at this point, which is the maximum point at point B, our acceleration will simply be our circular acceleration. So if we sum all the forces that are acting in the y direction, so if we take that to the y, remember your frame of reference, and if upwards is positive, summation of forces in the y direction, we have Fn. Mg, remember, is acting in the negative y direction, so it's minus mg. Okay? And this should give us the mass times the acceleration, and the acceleration in this case is circular, so it's replaced by AC. However, remember that it's negative since it's pointing downwards, and we've chosen upwards to be positive, so downwards is negative in this case. So our acceleration, in fact, it should be negative AC. So therefore, the normal force minus the weight, which is mg, should give us the mass times the circular acceleration. If we look at that, we know that our circular acceleration is just given by v squared over r. So if we replace that into this, we'll remain with Fn minus mg is equal to minus m, then v squared over r. Okay? So we have Fn, making Fn subject, we have Fn is equal to mg, if I take that side, the weight on the other side, minus m v squared over r. But the condition here, we are being told that we need to find the maximum height that is required for the roller coaster to keep track of its track, so that it does not fly off as it goes up the uphill. So the only condition that we have, we need to meet a certain condition in order for the car to fly off, and that condition, the normal force at that point should be equal to 0. Therefore, we know that mg is equal to m v squared over r. If we cancel out the m's, we will remain with v squared is equal to g over r. And if we make, okay, we don't need to make subject of formula, that's fine. Or if we want, we can say v is equal to square root of g over r. Okay. Just a moment, sorry, I made a mistake somewhere. So the condition to keep the roller coaster up the uphill without it flying off, the normal force should be equal to 0. So if we put normal force is equal to 0 in that equation, I'll have 0 is equal to mg minus m v squared over r. Yes. So if I make v squared subject to the formula in this case, I'll just say m v squared over r is equal to mg cancel out the ends, I'll have v squared over r is equal to g. If I make v squared start with the formula, I'll have v squared is equal to g r. And that gives me the velocity at that point. Having found the velocity at that point, I'll go back to my original equation that requires me to substitute for v. Remember that the velocity at that point is just vb. Okay. So going back to my conservation of energy equation that I found earlier with an unknown vb, now that I know what vb is, I can just substitute this into that equation and it will be set. So that equation was given by g h max is equal to g r, remember r is the height in the second equation, plus half v squared. Okay, v squared was determined to be equal to gr, so replacing that in that equation, I'll have g h max is equal to gr plus half, what's the value for v squared? It's gr. I already found v squared by analyzing our rough stuff on that point. So if we cancel out the g's, those are popular, we'll remain with h max is equal to r plus half r. Therefore, h max is just equal to 3 over 2 r. So this is the expression that we need to find with respect to r in our question. And the question now proceeds by telling us that what would be the highest height, or rather the maximum height, if we are given r to be 10. So if r is given by 10, if r is given by 10, so we have h max is equal to 3 over 2 r, which is 3 over 2 times 10. Therefore, h max is equal to 15 meters. So our height should be 15, our maximum height should be 15 meters in order to keep the roller coaster down the valley and up the uphill without allowing it to fly off. So we are done with question 2. We now proceed to the next question, which is question 3. A moment, I just get the marker. Okay, question 3. Question 3. A few moments to read it out for you guys. Okay, so in question 3, we have been given this scenario. So there is a spring that attaches itself to a block. Okay. And then the block is stretched. So the block so the spring is compressed to 15 centimeters. Okay. So the block is compressed to 15 centimeters, and the block is 200 grams. And then after that, it's shot off and it's allowed to move on a frictionless horizontal surface up an incline. So our incline is not frictionless at an angle. So this thing is moving at an angle of 45 degrees. And then the height of the incline is given by 2.0 meters. Okay. So we are being asked to find D. So we need to find the path that the block will take. So we need to find D, which is that. Okay. So how do we proceed? So in the figure below, a spring, we've been given a spring constant of 1000. So our spring constant K is given by 1000 Newton meter. Okay. And our block is 200 grams. So the mass is equal to 200 grams. Converting that into kg, because we want to work with SI units, given the spring constant to be newtons and meters. So our block is just 0.2 kg. Okay. And then our compression is 15 centimeters. So that is our displacement, which is x, is given by 15 centimeters. In meters, that is just 0.15 meters. Okay, then we've been given the kinetic, the coefficient of kinetic friction of the incline. So our incline is not frictionless. Remember that our horizontal surface is frictionless up to that point, but as the block moves up the incline, this thing has friction. Has a friction coefficient given by mu is equal to 0.2. So we are being asked to find the distance D that the block covers. So as the block moves on a horizontal surface up the incline at 45 degrees, we need to find the distance D that the block covers before touching the ground. So the ground is here. So if you look at the movement that the block will move, that is projectile kind of movement. So in this question, we need to combine the work energy theorem together with projectile motion. So I would suggest that you revise your projectile motion, otherwise you will find difficulties in sorting out this problem. So as usual, having collected our data, let's proceed to the analysis of our system and the block. Okay, so apply conservation of energy. Remember the topic is conservation of energy. So apply conservation of energy. And in application of conservation of energy, we know that the initial total energy should always equal to the final total energy. The total energy in this case is given by the work done in compressing the block. So the work initial plus the potential energy of the block, which is initial, plus the kinetic energy of the block, which is the final, or the initial rather also, should give us the work energy that is required to move against friction as it moves up the incline. So the work energy final, which is the frictional work done, plus the potential energy as it moves up the incline. So potential energy final plus the kinetic energy again as it moves up the incline. So that is my final kinetic energy. So the work done in compressing the system is just 0. And the potential energy in this case is the potential energy that is stored in the system with regards to the spring. So that is given by half kx squared plus the kinetic energy in this case at our initial point is just 0. So that should just be 0. Then that should give us the final work done in moving against friction, which is the frictional force, is given by the frictional force times the distance. Remember, okay, in order to reduce on the ambiguity there, let's use L, where the L is this distance up to that point, because that's the distance that you need to calculate, or rather that you need to multiply with the force in order to find the work done as it moves up the incline. Then plus the potential energy at that point is given with respect to h, because our h is there, so it's just given by mgh. Then plus the final kinetic energy, which is given by half mv squared. Looking at our final equation, we look for the components that are missing in order for us to evaluate our system. So we have K, we have been given X, we don't know the friction force, so we need to find that. We need to find L, which is easy because we have an angle here and we have the height h, so by Sakatoa we can easily find L. Then we also have the mass, which is given to us. We know what gravity is. H is simply given by 2. M we know in that case as well. Then we have to find V, because we don't know the velocity that the block will have at that point. Okay, so let's find the frictional force, and then we also find the velocity as our object, or rather as our block moves up the incline. And when we find those things, we'll easily find the distance d that is required for the block to fly, or rather to sail, before it touches the ground. Okay, so let's analyze our block as it moves up the incline. Okay, and also delete that. So if this is my incline, remember the forces. So if my block, let's put our block to be on that point, and if this is my angle 45 degrees, I know that the mass, or rather I know that the forces that are acting on my block are given by the weight, which always acts downwards, and then there is the normal force, which acts perpendicular to the surface, facing upwards. And then we have to resolve the components of mg. So the components of mg, I know that that angle is 45 degrees, and mg in this case is mg cos 45. Okay, so having found that, I know that summation of forces in the y should give me the normal force, which is Fn, plus mg cos theta, which is acting downwards, cos 45, so that is minus mg cos 45 degrees. And that should give us the acceleration ma in our y direction. Okay, in our y direction, we know that the acceleration is simply 0, so therefore Fn is given by mg cos 45 degrees. Okay, what next do we need to look at? So therefore, from that analysis, we can easily tell that the frictional force that is appearing in our energy weight conservation theorem is simply given by mu Fn. In this case, Fn has been determined by the block on the incline, so Ff is equal to mu Fn given by mg cos 45. So we have those quantities. Okay. So now that we have those quantities, and we know that L from this point, L is just given by h, which is the height, divided by sine 45. So when you figure out SOHCAHTOA, you come up with that. So replacing all those quantities that we find in our energy work theorem, we'll end up with something that looks like this. So we have that quantity there. So remember, our energy theorem was given by the potential energy contained in the spring, which is kx squared is equal to, and then we had the potential energy at the top, which is mgh, then plus the kinetic energy at the top, which is mv squared, plus the work done, which is in moving against friction, which is given by the friction force times the distance. The distance in this case is L, so we decided to name that L so that we don't confuse it with the D that we need to find later on. Okay, so we determine FF and we know what is L. So replacing those quantities, we have kx squared is equal to mg h plus half mv squared plus FF is given by mu mg cos 45 multiplied by h over sine 45. Okay. H, remember, is just 2, the height. So that is found by SOHCAHTOA. And when we solve for V, we need to solve for V. So solve for V. So that is just simple algebra. I'll come up with V is equal to square root of x squared over m k minus 2gh, then minus 2 mu mg cos 45 multiplied by h over sine 45. So all this thing is in the square root. When I look at my final expression, so when you do simple algebra, you just make V subject the formula by getting everything that is this side on the other side, and then leave V on its isolate V, you end up with this. If you look at this quantity, we have X that is given, we have M that is given, we have K that is given, G we know, H is the height 2 here, so that is my H. I know what mu is given by 0.2, I know what M is, the mass of the block, G I know, cos 45 I know, H, remember that H is that, so that is easy, sin 45 that is easy. When you solve for V, when you replace all the quantities in, expect to find the value for V to be, so the value for V in this case will be V is equal to 8.09 meters per second. So verify that with your calculators. So this is the speed that the block will have as it moves up the rank before it touches the ground. So we now know the velocity at which the block was shot at. So this is the V that we have just found. So having found V, you guys are experts in projectile motion. At this point, we can find D. D is just given by the X range of the projectile motion. So how do we do that? Remember that the velocity that we found is the resultant velocity. We have to break it down because at this point, our projectile, which is a blob, is moving with respect to the y. So it's moving with respect to the y-axis and the x-axis. Okay, so breaking down our velocity, remember that the angle 45 here is also the same angle 45 there. Okay, so if I break down the velocity, so my vertical velocity, which is Vx, is given by V itself, cos 45, which is the angle, and Vy is given by V itself, sine 45, which is the angle. I know V is 8.09, so if I replace that into that, I'll have 8.09 cos 45. And if I do the same to the vertical component of V, I know that that is 8.09 sine 45. So if I evaluate this, remember that cos 45 is the same as sine 45, so we expect to have the same values. And if I compute this, I know that that is 5.72 meters per second, and this will also give me 5.72 meters per second. So I know what my Vx is. So Vx is 5.72 meters per second. That's the vertical velocity as the projectile moves in that view, and then Vy is equal to 5.72 meters per second. So now that we have these components and we have x, remember x is our range, so that is just a change in x. That's what we need to find. So x is equal to d, and we need to find that. So if we employ equations of motion, I'm going to use s is equal to ut plus half at squared. My u is what I was finding here. So this thing is moving in the vertical direction. So in the vertical direction, I've been given the height, because we've been told that we need to calculate d before the projectile hits the ground. So therefore, the height is just the negative value for that. If we take upwards, it will be positive, then downwards is negative. So in this case, our s is y is equal to u. We are in the y direction, remember, so we are using the vertical component, which is vy, multiplied by the time, plus half. Remember that g upwards is negative, so this should be negative here. Acceleration becomes g, and then t squared. So if I put in the values, y is my distance, but it's going downward, so before it hits the ground, my y is negative, so it's going to be negative 2 is equal to Vy. I already found it to be 5.72 minus, rather multiplied by t, minus g is 9.8, and if I half it, it's just 4.9 t squared. So use the quadratic equation to find this. You know, the quadratic equation will be given by t is equal to minus b plus or minus the square root of b squared minus 4sc, everything over 2a. When you implement that, you find the value for t is equal to 1.45 seconds. The other value will be negative, so only take the positive value because time can never be negative. Now that I know what my time is, and I know that this is given by the x range, the x range is just given by the change in x, should give you the velocity in the x times the time in that. Therefore, remember Remember that the velocity in the x direction was found to be, so that is just d. This was found to be 5.72 multiplied by the time that we just found using the quadratic equation 1.45. When I do that, I expect my d to be 8.29, somewhere around there. So we are done with this question. We go to the final question. It is very easy. When you know the formula, then everything will come out. So I don't expect us to struggle much on the last question. On the last question, rather. So the last question, it's on power, and we hope and trust that you guys have exclusively done the power topic. So in this question, we've been told, so this is question 4, we've been told that a 20 horsepower electric pump, so we know that power is given by 20 horsepower. If I convert that, I need to convert this into SI units, so it's into watts. I know that 746 watts a horsepower. So that will just give me, something like 1,409.20 watts. Yes, so we are being told that the well is 10 meters in depth, and then the pump must do work such that it needs to pump water from the 10 meters. So this is my well. So that should be 10. And then it needs to pump this water to another distance 3 meters above. So to another distance 3 meters above in the tank which is there. So the total height is 13 meters. Okay? And then we've been given the volume of the tank, which is just 2,000 liters. Remember that 1 cubic meter is equivalent to 1,000 liters. So if I convert that into meter cubed, it's going to give me 2 meters cubed. So we've been told to find the time that it will take to pump water from the well into the tank. So in this case, we proceed by simple analysis by just writing down the formula for power, and then from there we'll build on whatever quantities that we need to find. Okay? So we know that power is given by the work done, which is just the energy, divided by time. But we need to find the time. So time is equal to energy over power. Energy in this case, remember that this thing is, the pump is pumping water from the well to the tank, which is 3 meters up, and then the well is 10 meters down. So what the pump is doing here, it's fighting against potential energy. So the energy in this case is just the potential energy, which is given by the mass, the gravity, and the height, divided by the power. But I don't know what the mass is. However, I was given the volume. So I know that mass is equal to, or rather the simplest way to figure this thing out is, we know that density is equal to mass divided by volume. So this implies that mass is equal to density times volume. And we know that the pump was pumping water, so the density of water is just 1,000 kg per meter cubed. So therefore mass is equal to density times volume, which is 1,000 kgs per cubic meter, which is a constant. You can look up that value. Multiplied by the volume is given by 2 meters cubed. So the cube and the cube go, I'll remain with mass is equal to 2,000 kgs. So this is the mass of water, and replacing it in our equation, I can find the time is equal to the mass, remember mgh, so just to write it down for you for clarity, mgh divided by power, mass we just found it to be 2000, times gravity we know it's 9.8, times height is a combination of the depth of the well together with the height at which the tank is placed from the ground up. So that is just 10 plus 3, which is 13, divided by power, we found it to be 1,409.920. So when you figure out the mathematics there, the time that it will take to pump 2,000 liters of water is 17.43 seconds. And that brings us to the end of our tutorial. So I hope you guys were following and revise as much as you can before your final year test and final semester exam rather. Okay, so from me, this is it. You have the next tutorial in physics. Hoping next week that will cover all the 2 remaining tutorials, and after that, you guys will be set to pass your physics 101 exam. Have a good day. Enjoy your lunch.